All right, welcome to ENGR 325, your last class. Try not to cry. Okay, so as we wrap things up, I just wanted to take care of some last few notes on supersonic nozzle flow, and we'll go from there. So last time we talked about the area Mach number relation. That's where we ended. Looked something a little like this. If I move over to my document camera. It'd come up with an expression like that. So we looked at how a change in area and change in velocity at a given Mach number, subsonic or supersonic, kind of affected each other, and said that, okay, if I have a converging duct, that is a subsonic nozzle, so my subsonic side, it's my nozzle. If it's diverging, that's a diffuser, meaning we can expect a positive change in speed through the nozzle and a negative change in speed through the diffuser. And in supersonic flow, those two roles are reversed. So a converging duct is a supersonic diffuser, and a diverging duct is a supersonic nozzle. Now, the question we didn't ask last time was, what if the Mach number equals 1? Well, if Mach number equals 1, all this here goes to 0. So that means that there's no change in velocity at all. The what's called area can do whatever it wants. Sorry, what I say is the velocity can change however it wants. There's no change when Mach number equals 1. They just call it cannot be a change in anything so long as Mach number equals 1. You can kind of think about it like this. Say I have subsonic flow. I speed it up to Mach 1 using a converging duct, a subsonic nozzle. So I speed it up to Mach 1. Well, if I want to accelerate it further, I probably converge this further, right? Well, if I converge this further, well, that's a supersonic diffuser. So I'm just going to bounce around there because this is going to want to slow me down because I've gone supersonic, going to Mach 1 here. Then as soon as I'm subsonic again, it's going to want to speed me up and so on and so forth. So I'm just going to stay at Mach 1 forever. You can think about it the same way if I started supersonic. I'll diffuse, I'll slow down. Oops, sorry. I'll slow down to the point where I'm subsonic, then it's going to make me go faster and slower and faster. So once you go sonic, meaning once your Mach number is 1, using one form of nozzle, you can't go past that. We're using the same geometry. And that's why when you look at rocket nozzles or jet engines, they usually take the form of a converging, diverging nozzle. So this is your converging end. Which is usually subsonic. This is your diverging end. Usually supersonic. And this thing in the middle is called the throat, which is usually sonic. So Mach number is 1. This is a converging diverging nozzle. So the idea is you throw flow in the front end here. It accelerates to Mach 1. Once it's at Mach 1, if I start to expand it using a diverging nozzle, that's a supersonic nozzle, right? So it'll continue to accelerate through Mach 1 and go supersonic. So the question is, how do we analyze all this stuff and kind of get back to what we were originally looking at, which was saying, well, if we have a jet engine whose exit nozzle changes depending on thrust output, what's going on? How can we compute parameters of interest like pressure? Because we know that pressure is important when we're talking about fluid flow, and a jet engine has all this sensitive subsonic gear upstream of where the nozzle is. So if we probably should figure out like what pressure at the nozzle is, because that's probably going to propagate upstream. So we need to do some work here, see if we can find something out about flow properties. So let's have a go at it. So we know that at the throat we have sonic conditions. So that's the starred condition that we were talking about a little while ago when we talked about isentropic flow. The other thing we know is that we're assuming that there aren't no shock waves in the nozzle for now. So that means that the entire nozzle flow should be isentropic, which means adiabatic and reversible, right? So it means we're assuming there's no viscosity, it's adiabatic, it's steady, and it's compressible. So let's have a go at this. All right. So we assume sonic conditions at the throat. We can write conservation of mass, something like this. Again, oh yeah, we're assuming quasi 1D flow. So U is my entire velocity. So this is the mass flow rate at the throat. And since m dot in has to be m dot out, know that that's m dot at throat equals the mass flow rate anywhere else. We know that, excuse me, at sonic conditions, U star equals A star by definition, since you are at Mach 1, and meaning that you're traveling at the speed of sound, or A or C or whatever your chosen variable for speed of sound is. So if we have that, we know from our isentropic relations that A over A star, or not from our isentropic relations, from the math we did last time, that A over A star, or the area at one part of the nozzle divided by the area at the sonic section of the nozzle, is equal to rho star, let's say C star, that's again that's speed of sound at sonic conditions, rho U. So just for clarity. So that would be like the section corresponding to that. That would be the section corresponding to the sonic conditions. Okay, so we got that. If we expand this using the isentropic relations, we get something that looks like this in terms of our stagnation densities, which, because we're isentropic, shall remain constant. So we got all that. Over here so I can look at enough things at the same time. Okay, move that up. There we go. All right. So we know from our isentropic relations, rho star over rho, 2 over gamma plus 1, 1 over gamma minus 1. So essentially, if I just take my isentropic relations for gamma, and I set Mach number equal to 1, I can get this. This is just a simplified form of, excuse me, this guy, if you remember it. We're just setting that equal to 1 because we're at our sonic conditions. So if we if we plug all this together along with our definition of sonic Mach number, which conveniently also has a relationship attached to it that looks like this. We put all these together. If you put all these together with this guy, we can get something that looks an awful lot like this. If we simplify it down. So we'll raise to the gamma plus 1 over gamma minus 1. And that is a more, how do I say this? An analytic form of our area Mach number relation. And this is in the end is what's tabulated in the back of the book in your isentropic flow tables. So if we pop over to slides again, if we apply this relationship through a nozzle, we can get something that looks like this in terms of property variations across the nozzles. So you start subsonic, you increase to the throat, which is at some sonic, which is at the sonic condition, which is where the nozzle immediately begins to diverge, so it accelerates, and you get this sort of a trend. Look at the same thing with the static pressure over the stagnation pressure, assuming we start at some quiescent reservoir of pressure. So the static pressure equals your stagnation pressure, and then the static pressure drops as you go out of the nozzle. Same thing with temperature. But let's go with this one for a second. Let's go back over to pressure. Why does pressure have to drop as you go through the nozzle? Why does static pressure have to drop as you go through the nozzle? Because another way of thinking about it is if I had a convergent divergent nozzle in my hand, it doesn't just spit out supersonic flow, right? It just sits in my hand. So there has to be something making the flow move. And when we talked about this in subsonic flow, in subsonic incompressible flow, and we said it again when we first started talking about compressible flow, we said that in order for velocity to, for there to be a flow velocity, there has to be a pressure gradient. So here's our pressure gradient. We start with some higher static pressure on the front end of the nozzle, on the inlet, and then we have some lower static pressure at the at the exit. Now the trick is, so there's going to be some static pressure here that we're going to compute based on flow movement through this nozzle, but at the exit we ultimately have to interface with like outside air, right? Like if I have a rocket engine, there's the air outside of the rocket engine that it's blowing that exhaust into, and there's the exhaust itself, and they're going to have two separate sets of properties that describe them. They're all going to have different pressures, different temperatures, densities, et cetera, et cetera, et cetera, et cetera, et cetera. And they're going to have to mix. So we're going to have to find. So we're going to have to look at how those interact. Excuse me. Okay. So before we get there, just to make sure that we're all on the same page, so if we know something about our exit conditions or our inlet conditions, we can figure out what our throat conditions are going to be. So for example, and vice versa as well. So for example, say that we have some converging, diverging nozzle. On the inlet side, we know that we have some quiescent reservoir feeding this. 1 atmosphere pressure and 288 Kelvin, so it's like usual sea level standard conditions. And this is the area, the cross-sectional area of the throat. And this is the cross-sectional area of the exit. We've designed this nozzle such that the exit is twice the area of the throat. So the question is, what's pressure and temperature at the throat and the exit? Because those be like important things to know, right? Not only to design this thing so it doesn't like melt or blow up, but also just in terms of what sort of back pressure are we dealing with, right? And to our earlier question, what sort of a pressure difference between the exit and the atmosphere are we going to have to deal with? So we know that velocity is approximately 0 in the reservoir. So these are actually stagnation conditions. Because this is isentropic flow, these stagnation conditions should remain constant throughout the entirety of the nozzle. Therefore, if I drop down and go to my isentropic flow tables, I can define P throat as find the ratio P star over P naught, multiply that by P naught, and I get my static pressure at the throat, right? Because the throat, by definition, at least it should be, and we're going to assume it here. Sorry, it's one thing I forgot. Is where her sonic flow occurs. So the star condition is there. So as a result, I get 5.28 atmospheres at the throat. I can do the same thing with temperature. Find T throat as a function of T star or T naught from the isentropic flow tables, divided by T naught, and get like 240 Kelvin. At the same time, if I look at going from the throat to the exit, it's now the same thing. I just have to look on the table for the Mach number where A over A star equals 2. Turns out that that's Mach 2.2. So then I can just read the ratios of stagnation pressure to pressure, temperature to stagnation temperature off of the table and get that static pressure at the exits 0.94 atmospheres. So there's our pressure gradient. The temperature at the exit is 282.9 Kelvin. Cool. So that's that. Relatively straightforward. Now this is all well and good, but as said, like what happens with this as we move through the atmosphere, like our hypothetical rocket motor? We start on the ground at more or less sea level. Air is pretty thick here. Pressure is relatively high. Then it goes to like 80,000 feet. Pressure is very, very low. Not much air density either. How does this the exit part of the nozzle change and how it works? How does the change in ambient conditions affect the operations of the nozzle itself? Okay, so let's think about this. If we decreased the pressure at the exit, so the ambient conditions around the nozzle. I have my nozzle here. If I decreased the pressure back here that the nozzle is blowing into, what's going to happen? So first thought is like it would be a greater pressure gradient, right, from the start to the end, right? So I'd like make flow move faster, right? But we have this throat area. We said that no matter what, you can't go faster than Mach 1 using the same geometry. Like no matter how much I neck this puppy down, I'm not going to get beyond Mach 1. I have to expand again once I hit Mach 1 in order to go faster. So the interesting thing about decreasing pressure down here is that it can't make the throat get any faster. The result, like you have to remember, like everything's governed by area ratios, right? So it's not necessarily going to make this whole nozzle go any faster. Like it's not going to increase the mass flow rate through this nozzle. After a point, everything is just the same. So sorry, I'm trying to find a slide here, but it's not working. So I'll draw it. So this is what's called the choked condition. So if I drew a graph and have m dot mass flow rate on the vertical axis and exit pressure on the horizontal axis, what I'd see is that after a certain point, m dot is constant. As I start to dial back my exit pressure, what's called the mass flow rate actually becomes a constant. And this is what's called choked flow. You simply cannot make the engine go any faster because the mass flow rate is fixed by sonic conditions at the throat. You might think of down here, the throat is subsonic. And over here, the throat is sonic. Once it's sonic, mass flow rate's fixed. That said, that brings up another question. Can pressure variations propagate through the throat then? Will they ever get upstream once the flow is choked? So if we think back to our original discussion, pressure variations, they travel at the speed of sound, right? Well, the flow is moving at the speed of sound in choked flow by definition. So if the flow is moving at the speed of sound, it means as fast as the pressure variation is trying to go upstream, the flow is moving in the opposite direction. So the pressure variation can't move. It can't migrate upstream because the flow is moving downstream as fast as the pressure variation is moving upstream. So no pressure variation down here will travel through the throat. It won't get any further than the throat, which is also kind of interesting. So the whole everything upstream of here is kind of protected by the fact that the flow is sonic here, provided that this is a choked nozzle, meaning that flow is sonic here. So that's kind of cool. But let's go the other direction. So we talked about turning our exit pressure down. So okay, so that means that crank that down. We have choked flow, and the nozzle is going to want to try to deliver air at the same pressure as is at the exit, right? That's what it's going to want to do, because else, if the pressure here and pressure here, the ambient pressure, or maybe we can say the back pressure, would be a better term for it. If these aren't equal, then either air is going to be trying to go into the engine, or it's going to be trying to like wrap around the outside. And we know that both of those things don't happen. So there has to be some mechanism by which the pressure at the exit is corrected to meet the pressure here. So if the back pressure is really freaking low, it means that air density is also probably really low. If you pop over to the slides, so the nozzle is going to try to expand that which is called the flow. It's its flow to meet that, right? But there's a limit to it. And we've seen the slide before when we first started talking about compressible flow, and we said that there's some limit to how low our density can get, some limit to how low our pressure can get, until nature corrects things, and corrects it with this thin distortion that has an immediate jump in pressure and density, which we said was a shock wave. In this case, it's a little curved, but you can approximate it as a normal shock inside of the nozzle. And this is when your back pressure is sorry. And this one, sorry, I did this back. I did this back. I did this backwards. This isn't for your low back pressure case. This is for your high back pressure case. Sorry, I had that backwards. This is for having lots and lots of back pressure, because the back pressure is so high that in order to equal that back pressure, the flow needs a shock wave in order to get the pressure in the nozzle high enough to equal the back pressure. And as a result, a normal shock occurs inside of the nozzle in order to jack up the pressure at the exit, in order to jack up that quantity there so it can meet the back pressure. Now, what if I turn down my back pressure a little bit? Well, now I don't need a normal shock to do that. Maybe I just need an oblique shock in order to do that. This is what's called an under-expanded nozzle. What if I turn down the back pressure a little bit more? Well, now eventually I'm going to hit a sweet spot where the back pressure and the exit pressure match, and that's perfect. It means that my flow just leaves smoothly from the nozzle and there's no extra flow structures required. Eventually I'm going to hit an overexpanded nozzle. And if you watch a rocket launch, this is when they're like in space, right? Or when they're in the upper atmosphere and the flare from the from the rockets starting to spread out means that the exit pressure at the nozzle is much higher than the back pressure. So you have these expansion fans forming instead. You might ask, okay, but why do we care? So let's start with shock waves. Well, we know that shock waves cause a lot of drag, right? And drag is something that we don't want. So we just call it because the flow has to slow down significantly at this point. If this is a rocket nozzle, I want to chuck things out the back of this as fast as I can. Or if this is an F-15 jet engine, I'm going to want to chuck things out the back of this jet engine as fast as I can. These normal shocks slow it down. So I'm not getting as much thrust out when I have these things here. With the expansion fans, sure, we've seen it expand the flow. Well, that means that but that also means that there's like an adverse pressure gradient now, right? This is also going to create some drag for me. The best case is here. When we don't have an expansion fan, we don't have any shock waves, but we have to be able to match pressures at our exit and at the outside in order for this to occur. So if you think back to our F-15 jet engine, that nozzle changed shape based on how much thrust was putting out, right? How much thrust is another word for how fast flow is leaving the engine or how much pressure is there. So it's changing its geometry so that it can better match the ambient pressure, right? Because this how much that nozzle is opened or closed, that's going to change the pressure, temperature, velocity of that exhaust, so that it can better match whatever the ambient pressure is, and give you the most efficient jet engine. So that's that. That is your introduction to subsonic and supersonic nozzles full flow. That's all I got for today. Test is on Tuesday, 8 a.m. right here. And shall note that nozzle flow will not be included on that test. And that's all I got for today. Thanks for stopping by.